Okay, this is question 3, and for the very first question, we are told to estimate the acceleration, and hopefully these are starting to become a little bit more familiar with us. Now we do need to show our work, and we also need to indicate our units of measure. Now do notice that we are given the velocity of the particle. Here we're told that it's differentiable, so do keep in mind if you're told that the function is differentiable, you may assume that it is also continuous, and I would make myself a note there because you never know when that might pop up. Alright, so we're also given a position maybe. Let's see the position of the particle. X equals 7 when t is 0. This is also important. Every part that they give you, you will use somewhere. So, let's see. If we're going to find or estimate the acceleration at time 36, so we're going to estimate, so I'm going to say A at 36 is approximately. And now we need to go find between what two values would 36 fall. And hopefully we see it's going to fall somewhere over in here. So we're going to have V at 40 minus V at 32 all over 42, or 40 minus 32. And so notice we're going to have 7 minus a negative 4, so 7 plus 4 all over 8. And you're welcome to stop there, and I'd really rather you stop there. That way you don't miss add or anything. And so our units, that's going to be meters per second, or per second squared. Alright, so this is going to be worth 2 points. This was a 2-point problem, and it's 2 points I hope everyone gets. Alright, so for part B, we are asked to, 1, explain the meaning of this integral, and then we are asked to also use the trapezoidal sum with 3 subintervals from 20 to 40 and to approximate the actual value. So a good reference here for us to remember, if you integrate, you're removing a rate. So we are integrating v at t, so really that just removes the per second, and that gives you a good idea of what you're finding. You're finding the meters that the particle moves. So for this first part, or part B, if we're going to interpret what our integral is, then we can say, well, the integral from 20 to 40 of v at t dt is the distance. So again, distance in meters. The particle travels over time, or during time, or maybe during. And then our time frame, always make sure you use your time frame, which is going to be your limits of integration. So during the time 20 less than or equal to 40. So there's where we have gone through and interpreted. It's the change in position, or it is the distance there in meters. Alright, so now let's go ahead and actually find our trapezoidal sum. And keep in mind, you're just going from 20 to 40. So again, we're going to set up that approximation. So I'm going to come over here to the side from 20 to 40 of v at t dt is approximately. And then we have to keep in mind our trapezoidal sum is going to be 1/2 the height, which is the difference in the x values, so, or the t values for this problem. So the difference, and again, when you're looking 20 to 40, so the difference there from 20 to 25 is going to be 5 times the sum of the bases, which is going to be my two y values, or my two v at t values. So it's going to be negative 10 or 18, sorry, plus, and then the next one, 1/2 times 7 times negative 12, and then plus, and then 1/2 8 times 3. And it's perfectly okay to leave this value here. We do need to indicate our units of measure, so that would be in meters. So I wish I had some room here. If you do, just put it here at the end, meters. So we have that. Or if you really wish to simplify the sum, I wouldn't do a tremendous amount. Half of negative 18 is negative 9, so negative 45. And then this is going to be minus 42, and then plus 12, and then that's all going to be meters. But I would not go too much further than that, and I would probably leave the problem like that up there. Alright, so the next part of this, between 0 and 40, must the particle change directions for any of the subintervals indicated by the data in the table? So changing directions, our particle will need to come to rest before it changes directions. So let's look up at our chart and see, and if we notice, we have some sign changes going on. So notice that between 8 and 20, we have a sign change there, times 8 and 20. And then also between times 32 and 40, we have a sign change. We go from positive to negative there. So that tells me my particle changed directions there. So we have to really justify our reasoning. And anytime you see this, and it's really asking you, does the value exist? That's going to be our intermediate value theorem. So we do, in order to use the intermediate value theorem, we have to state the conditions or the rules of it, and that's where we're going to use this whole continuous idea. So our reasoning, since v at t is differentiable, and it's okay to say it there because we just named it. It is also continuous. So that's important for us to state because we're setting up the conditions for that intermediate value theorem. So again, since v at t is differentiable, it is also continuous. And then the intermediate value theorem, that's guaranteeing if we have a y value, we're guaranteeing an x to go with it. So by the intermediate value theorem, there must exist a t. So there must exist a t, time t is what I would put, a time t. So, well, a time t over the interval, and notice, let's see, the intervals that we stated, we're going to, a time t, and then that t value's got to be between 8 and, where was our sign change? Between 8 and 20. And there was one more, so we've got a couple of intervals here. And I think the other was 32 to 40. Okay, so that has to exist. Let's see. Because v at t changes signs over these intervals or on these intervals. There you go. Okay, so that's another 3 points here, or 2 points here. So again, we're just stating our intermediate value theorem in the context of the problem. All right, now for part D. So we're told that we have an acceleration of the particle is positive from 0 to 8. Explain why the position of the particle at time 8 seconds must be greater than 30. So keep in mind, let's see, if we look up, we're just looking from 0 to 8. And so I know the absolute smallest value v at t ever was through there is going to be 3. If we look at our chart, we see that is the smallest value v at t could ever be. And let's see, and let's throw back to the, well, I do know that if I integrate v at t, so let's also talk about if we integrated v at t from 0 to 8, v at t dt, that's going to give us our position at 8 minus our position at 0. And so let's see, that is talking about our bounded area there. Also, keep in mind that when we integrate, we also talk about a bounded area. And let's see, what would be that maximum bounded area? Well, the maximum time that you would go over would be 8. And then, let's see, the height, well, we already saw that would be 3. Okay, so that's the highest it'll ever be. That's the maximum part. Okay, and so here, that's the biggest it'll ever be for the velocity. Well, then let's see. So if we're talking about the largest this is ever going to be, and we're really looking at the bounded region, we're looking at that area, 8 times 3. And so the biggest that's going to be is 24. But that's also equal to, and we're looking for our position at 8 minus, and our position at 0 we were told earlier is 7. So that shows us that our position, if we solve that equation, our position at 8 is actually going to be 32 meters. So here we've shown that our position at 8 must be greater than 30. Okay, number 4, we're asked to pinpoint the maximum acceleration over this closed interval, and we're given velocity. So we need to go find our acceleration. So we have 3t squared minus 6t plus 12. Now, if we're going to talk about maximum acceleration, we're talking about a maximum value. So we have to see where our derivative, which is our acceleration, equals 0. And then we also need to find our endpoints here. So our acceleration, if we let that be equal to 0, we can factor out a 3. So we're going to have t squared minus 2 times t plus 4. And so notice we have a parabola over here. And we do know that over a parabola, it's probably going to look something like this. And so we know as we tend toward infinity, x's tend toward infinity, our y values tend toward positive infinity. So the end behavior here is positive, and it's increasing, it's constantly increasing here. This will not factor, and I think it has imaginary roots if we go through. So really, that maximum value is going to have to occur at 3. So we need to go find a at 3. And so now if we did not know what the shape of this graph was going to be and such, then we would have to go through and test all of our values. If you know what those graphs look like, that should save you some time here. Alright, so we're going to get 7 times 3, which is 21, so you should have answer choice D. All right, number 5. We have a particle moving along the x-axis. So that at its time, we've got our position. For what values of t is the velocity of the particle equal to 0? So we're going to have to find the derivative of our position. So we're going to have to find x prime at t. And so looking at that, we're going to get 2 times t minus 6. And we want to know when that velocity of the particle is 0. So 0 equals 2t minus 6. So it looks like t is going to have to be 3. All right, so for the next problem, number 6, a particle moves along the x-axis, so that is acceleration. So I have a at t equals this nice little linear function here. So we have that for a at t. If the initial, velocity of the particle is 6. So notice it said if the initial velocity. So initial, so that tells me the time is 0, and so the velocity is 6. So we have some initial conditions. During what time t is the particle farthest to the right? And we know the particle is moving right when the velocity is positive. So we really need to come up with a velocity function here. So if we have acceleration and we need to get to velocity, we need to integrate a at t. So I need to integrate 2t minus 7 dt. And so that's going to give me t squared minus 7t. And let's see, that is going to have to be a plus c in this situation because I don't have any endpoints. Please don't try to plug these in. You can go this route with it. And we know when time is 0, the particle's at velocity is 6. So that's going to lead me to the problem t squared minus 7t, and then that's going to be a plus 6. Well, now that we know what our velocity looks like, let's see where it's going to be equal to 0. So I have t squared minus 7t plus 6. If we factor this, we're going to get t minus 6 and t minus 1 equal to 0. And so let's look at this. We're trying to figure out, so we've got this acceleration function, and we're trying to figure out, well, where is this particle farthest to the right? Well, we know at 1 and we know at 6 the particle comes to a rest because that's where my velocity is 0. We also know that the shape of this graph is a parabola, so we also know that bad boy should be doing something like this graphically. That's what this equation should look like. So if velocity is positive, we're traveling to the right. Negative, we're traveling left. So let's look at what this little particle is doing at 1 and at 6. So over our time frame, we see that from 0 to 1, our particle is traveling to the right just because our velocity is positive. But notice that once that particle hits 1, comes to rest, it turns around and goes back this direction for quite a bit of time. For all of this through here, our particle's traveling left. And then once it goes through that same time frame, the particle's going to turn back around and continue from here all the way back. But now we have to be careful because we did have a set time frame. We said from 0 to 4. We wanted to know when the particle was farthest to the right. And so it looks like at t equals 1, in this area right here is where the particle is farthest to the right. So then that tells me my answer choice is probably going to be B.